Hello, everyone, and welcome. Today we are diving into integration, but I want you to forget everything that sounds complicated about it. We're going to approach this like a detective story. See, with differentiation, you're given a function and you find its rate of change. Easy. But integration, it's all about working backwards. We already have the answer, the derivative, and our mission, our case, is to find the original function that it came from.
Look, you've done this a million times, right? If the function is x squared, you know its derivative is 2x. But what if we flip the script? What if we start with 2x and I ask you, hey, where did this come from? What was the original function? Answering that reverse question, well, that is the entire heart of integral calculus. So, think of it like this. Finding a derivative is like knowing a car's speed on its speedometer at one exact moment. But integration is the full story. What if you know the car's speed at every single moment of its journey, and you need to figure out the total distance it traveled? That's what we're doing here. We're working backwards from a known clue, the rate of change, to uncover the bigger picture. And this original function that we're searching for, it actually has an official name in our investigation. It's called the antiderivative. It makes sense, right? It's the function that existed before we did any differentiation. You'll also sometimes hear it being called the primitive function. Okay, so our mission is clear. Find the antiderivative. So how do we even start this investigation? Well, the best way is to use what we already know inside and out from our study of derivatives. We're just going to look at it in reverse. Here's the most important rule of the game. An antiderivative, let's call it a capital F of x, is any function whose derivative is the small f of x we started with. And this gives us a perfect way to check our work. If you think you've found the antiderivative, just differentiate it. If you get back to the function you started with, you've cracked it. Let's look at a really familiar example. We know that the derivative of sine x is cos x. So if we just work backwards, what's the antiderivative of cos x? Well, it has to be sine x. See? It's literally just the reverse process. Nothing new here.
And this reverse thinking works for power functions too. Remember, for derivatives, you multiply by the power and then reduce the power by 1. So to find the antiderivative, we do the exact opposite in the reverse order. We first increase the power by 1, and then we divide by that new power. That's why the antiderivative of x squared is x cubed divided by 3. Try differentiating it. You'll get right back to x squared.
And of course, we can't forget our special friend e to the power of x. Its derivative is, well, it's just itself. So it's only natural that its antiderivative is also itself. It's a special case, it's its own derivative and its own antiderivative. Pretty cool, huh? All right, our detective story is moving along nicely. But every good story has a twist, and we have a major one coming up. It turns out, for any derivative, there isn't just one suspect for the original function. There's a whole family of them. Let's go back to our very first clue. The derivative is 2x, and we said the antiderivative is x squared. But hold on a second. Is that the only possible answer? Just take a moment and think about that. And here is the plot twist. The derivative of x squared is 2x. We know that. But what about the derivative of x squared plus 5? Remember, the derivative of any constant is just 0. So the answer is still 2x. What about x squared minus 100? Same result. Any constant we add or subtract just vanishes when we differentiate. So what does this mean? It means we're not looking for just one function. We're looking for an entire family of functions. Picture the graph of y equals x squared in your mind. Now imagine just sliding that whole graph up, or sliding it down. The actual shape of the curve doesn't change, right? This means the slope, the steepness, at any x value stays exactly the same. All these parabolas, just shifted up or down, all share the same derivative. So how on earth do we write down an answer that represents this entire family? Well, we introduce a new character into our story, the constant of integration, which we write as a simple plus c. Here's an analogy for you. Think of the derivative, 2x, as the final viral TikTok dance. The antiderivative is the original choreography, but you could do that exact same dance in your bedroom, in a park, or on a stage. The location is like the plus c. It changes your starting point, but the dance moves, the derivative, stay exactly the same. So, plus c covers all the possible starting points. Okay, now that we've uncovered this whole mystery of plus c, it's time to learn how to write our findings using the official language of mathematics. This is how we write the official detective's report using symbols, so let's get comfortable with it. Let's break this down so it's not scary at all. This long, stretched out S shape, That's the integral sign. The function inside it, f of x, is called the integrand. That's the function we're integrating. The dx simply tells us which variable we care about. In this case, it's x. And the whole answer, capital F of x plus c, which represents that entire family of antiderivatives, that's called the indefinite integral.
So let's put this new language to use with our example. When you see this expression, the integral of 2x dx, it's just a formal mathematical way of asking our detective question. What is the entire family of functions whose derivative is 2x? And now we know the complete official answer. It's x squared plus c.
So we have this whole family of suspects, right? But what if we need to find the one specific function? What if the case requires us to identify the single culprit, not just their entire family? Well, for that, our detective story needs one last clue. This final, crucial clue is called an initial condition. It's basically one extra piece of information. It gives us a specific point, an x, y coordinate, that our function absolutely must pass through. This is the key that lets us find the exact value of c and finally crack the case wide open.
Okay, let's solve a case together. We're given the derivative f prime of x is 4x cubed minus 6. We also have a very important clue, an initial condition, f of 0 equals 3. This tells us our function must go through the point 0, 3. So, step 1, we integrate f prime of x to find the family of functions. The antiderivative of 4x cubed is x to the power of 4, and for 6, it's 6x. So our general solution is f of x equals x to the power of 4 minus 6x plus c. Now for step 2, we use our clue. We substitute x equals 0 and f of x equals 3 into our equation. So we get 3 equals 0 to the power of 4 minus 6 times 0 plus c. And step 3, that whole thing simplifies to just 3 equals c. And just like that, we found the exact value of our constant.
Now that we know c is 3, we can state the one specific particular solution. It is f of x equals x to the power 4 minus 6x plus 3. We've found our specific function. Case closed. So let's do a quick recap of the most important points. First, and most importantly, integration is just the reverse of differentiation. Second, when you find an indefinite integral, you're not getting one function, you're getting a whole family of them. Third, to represent this family, you must always remember to add plus c. And fourth, if you're given an extra clue, an initial condition, you can use it to find the exact value of c and nail down one specific function. The one thing I really want you to take away from this is that you are not learning something totally new and scary. You're just taking what you already know about derivatives and looking at it backwards. It's a new way of thinking, for sure, but it's built on a foundation you have already mastered. You've totally got this. And that wraps up our investigation into integration. But here's a final thought for you. We now have a powerful tool to work backwards from any rate of change. Just think about what that means. We could figure out a rocket's entire flight path just from knowing its velocity, or predict a country's population in 10 years just from its current growth rate. The real question is, what kind of mysteries will you solve with this? Thanks for joining me.